true model, right? And we want to estimate expected error. The error of this of our learned model is basically the ratio of the distance between the learned model and the true model versus the distance from the domain of the input. Right? Okay. Okay. Let's see what active learning would do. So one active learning approach that's very successful in this regime, where it's noise-free and just a single feature, and you know that the model's separable, is binary search. So we hypothesize first that the model is in the middle of the interval, and we query for a label in the middle of the interval. So we don't sample randomly from the distribution. We query sort of actively, and we get a label that's positive. Okay, that means that the true boundary is somewhere over here, right? So then we propose the midpoint between this label and edge of the boundary. And now we query a label for this data point. We see that it's negative. Okay, so that means that the true boundary is between the red point and the green point. So we propose the midpoint, get a label, propose a midpoint, get a label, propose a midpoint, and so on and so forth. Right. Okay, so now in 5 examples, we got about as good as we did in the passive learning case, where I think I sampled like 15 examples, something like that. And in general, for this very simple setting, very clean setting, you can prove that the number, if you want to be within epsilon, here's of the true model, so epsilon in the simple case you can think of as a generalization error, right? If you want to be within epsilon of the true model, passive learning requires order 1 over epsilon, right? Samples, we've drawn uniformly at random from this distribution. Active learning requires log of 1 over epsilon, so it's exponentially less data required. In practice, of course, people want to do active learning on high-dimensional representations, maybe multi-class, maybe structured labels. But and people try strategies, following this principle. Maybe not binary search. So the more general principle of this binary search is you look at the region of maximal uncertainty, right? At each point in binary search, you're basically saying where is the point where if I collected a label, it would be the region of highest uncertainty. Right? And so this notion of uncertainty-based active learning is very popular. You could generalize it to sort of binary, high-dimensional linear models, a multi-class classification, even structured labels.
In fact, if your strategy is based on uncertainty quantification, then you kind of assume you know the underlying distribution of the data.
You can. So it turns out. So one, if you're in a Bayesian approach, then yes, you're making that assumption. Let's say I'm fully probabilistic, and I have a Bayesian prior over then you are making that assumption. 2, it turns out that you don't need to make that assumption. You could prove you can't always prove, but you can sort of you can collect a bunch of data first, right? And then use that data as an empirical sort of uncertainty sampling. So you can be frequentist as well. So for example, basically every company does active learning these days. If they want to build a data-driven classifier of something. When you do active learning, you have to be a little bit careful about how you use that data, training data, because the training data is no longer sampled IID from the test distribution. Yeah.
So for something like high-dimensional, like an image, are you looking for? Is it like trying to sample examples that you don't predict well on, or something like?
That's one way to do it. Like if you're doing, let's say, multi-class classification, and you get this image, and you have this unlabeled image where you think it's 50% dog, 50% train, you might ask for the label. Your current model thinks it's. That's one way. That's one approach to active learning. There are cases where that fails, like you can construct pathological examples where that fails. Although in practice it tends to work okay. A lot of people use it. Yeah, it's not clear the pathological cases where it fails on like how often that arises in practice. Okay, so let's talk about the next topic, multi-armed bandits. So what are some problems with crowdsourcing? Well, it assumes you can label by proxy, right? If someone else labels these objects in the image, like they can say, there's a cat in this image, everyone else would agree that there's a cat in this image, more or less, right? But sometimes you can't. Sometimes you cannot do label by proxy, right? So for example, if you want to train a personalized recommender system that personalizes individual tastes, well, you can't ask the crowd what I'm interested in, right? The crowd cannot provide annotations for what I'm interested in. The only person who can really provide the annotations for what I'm interested in is me, right? So you need to ask the user whether a content is interesting or not, right? Also applications to personalized medicine, right? You can't ask the crowd based on sort of specifics of my physiology whether some medicine will work on me or not, right? I mean, you can to some extent, but at the super fine level of granularity, you cannot. It has to be the final verification needs to happen with the person you're personalizing to, or the population you're personalizing to. Right? So it requires the actual target of things. It cannot be done sort of offline or as a side sort of thing. Right? So here's sort of what the situation looks like if you're doing sort of clicking personalized labels, right? So let's say you're training a recommender system. And this is a real system, and it has a bunch of articles, let's say, that are unlabeled by this user as interesting or uninteresting. Let's say, for simplicity, the user can say thumbs up or thumbs down, right? Then the recommender system chooses an article, recommends it to the user. Let's assume the user gives it a recommendation, gives it a feedback, thumbs up or thumbs down. This is a label that we can use to add to our label training set to learn a better model of the user, what the user likes. So now we just replace the crowd with the actual end user, and this process repeats. So one question to ask is, well, what is the cost in this setting, right? Because we're not paying users money to use our system. What is the actual cost that we pay? How do we quantify how efficient we are? And that is what the multi-armed bandit problem seeks to formalize. So here's the formal definition of the multi-armed bandit problem. This is a very sort of simplified version of how you might think about modeling recommender systems. Suppose there are K actions or classes. So for example, you can think of each action as a sports article or a politics article, so on and so forth. Right? And let's say that each action, so this is K-class classification, no features, or in the feature-free setting. This is the average quality of a random article in sports, right? So every action has an average reward, user K. This is unknown to us because this is the user's private reward. It's unknown to us. We need to learn this from user feedback. And we'll assume without loss of generality that the K classes are indexed, are sorted so that the first class has the largest reward. Then how the multi-armed bandit problem works is it's an iterative learning procedure. It's an interactive learning setting, where at every iteration, the algorithm chooses an article from a class, so chooses an action, A, and it receives random reward, Y, that has expectation equal to the hidden average reward of the action chosen. So the algorithm is simultaneously making predictions and receiving training data, sort of in a closed loop process. And the goal is to minimize, and here's the cost. The goal is to minimize the notion of regret. So the goal of any system when it services real users is to maximize the reward that the user derives from using the system. If we did not have to do learning and we knew all the average rewards of every type of article a priori, we would always recommend the best one at every iteration, right? And this would be our average reward that we provide to the user. But because we don't know which action has the highest reward, we try some other policy and we learn on the fly, and this is the reward that we experience, right? And so this difference is what we want to minimize. So here is sort of a more cartoon depiction of this process in sort of as applied to recommender systems. So suppose that we have 5 types of articles. So again, 5 classes, 5-class classification, no features. So the 5 classes are celebrity news, economics, politics, sports, and world news. And let's suppose for simplicity again that every article belongs to exactly one class. Okay? So on day one, a brand new user comes to the system, and the recommender system, according to some policy, decides to recommend an article about sports. The user provides feedback, thumbs down, right? So now we've learned something about the user, right? And we get no reward, because the user didn't like it. Day two, the user comes back to the system and recommend one article. Let's say the algorithm, the recommender system, according to some policy, decides to recommend an article about politics. The user provides feedback, thumbs up. We learned something about the user, and then we got a reward. And then this process continues iteratively until the end of time. Okay? So this is basically sort of a cartoon depiction of the formal definition of the multi-bandit problem. Okay. At every time step, suppose we've run this algorithm for a while now. This is what we've learned about the user so far, down here. What do you think the algorithm should recommend at the current time step? Well, on the one hand, we can recommend an article about the economy because articles about economy, according to our current knowledge about the user, has the highest average reward. Right? So given what we know, this has the best chance of being liked by the user. This is known as exploit. We exploit our current knowledge. On the other hand, we have to sort of recognize that our knowledge base is estimated on a very small sample size. In particular, we don't even have any samples about whether or not the user likes celebrity news. Right? So in the worst case, we could be missing out on a reliable reward because we don't know. We simply don't know. And so the alternative action is called explore, which is to select the action whose subsequent feedback maximally improves the reliability of my knowledge base. Suppose the best action with the benefit of hindsight was to recommend an article of politics, right? If we had a lot of data, we would have realized that on average, the user likes article of politics the most. How do we sort of, trade off between this type of action and this type of action to converge to this as quickly as possible, right? In other words, how do you optimally balance the exploration and exploitation trade-off? And this is what's characterized by the multi-bandit problem. Whenever you have to do sequential decision making, where you don't know everything there is to know about the world, and you learn through actions, but you're also taking actions to maximize some reward, you have to balance an exploration-exploitation trade-off. And this is sort of one of the essential questions in interactive machine learning. So the way you think about sort of characterizing the efficiency of any algorithm is, on day one, an omniscient algorithm would recommend an article about politics because it doesn't need to do exploration, it doesn't need to learn anything about the user, it knows everything there is to know. Our algorithm, according to some other policy, recommends some other article, gets less reward. On day two, the omniscient algorithm recommends, that does not need to do learning, recommends the best possible type of article, gets some reward, we this time recommend the same thing, and so on and so forth. So the way you quantify the efficiency of any algorithm in this setting, the one way, is through what's called regret. And the regret is basically the difference in cumulative rewards between the omniscient algorithm and our algorithm, which has to do with some amount of exploration. Right? So you can think of regret as the opportunity cost of not knowing the user's preferences a priori. An algorithm in this setting is considered no regret if the average regret over time converges to zero, and the efficiency of how quickly this converges to zero is the efficiency of your no regret algorithm. So we want algorithms that, even though it doesn't know anything about the user, minimizes the opportunity cost of having to ask user questions about things that the user might not like. Right? So just to recap, you have k classes or actions, no features in the basic setting. Every class or action has some expected reward unknown to the algorithm. And then you have this iterative procedure where you choose an action, receive a random reward with this hidden expectation, learn something about these expectation, and you minimize this regret. That is the multi-arm bandit problem. Why is this called the multi-arm bandit problem? Well, like many things in life, it came from something frivolous. A slot machine is also known as a one-armed bandit, where you pull a slot and then you put in a coin, you pull a slot machine and see what your payoff is. Suppose that we have many slot machines. Each arm has a different hidden payoff. And the multi-arm bandit problem is to minimize the regret of pulling slot to arms. So you want to lose money as slowly as possible. What are some implications of regret? Well, if regret grows linearly with respect to the number of iterations, then the average regret is constant, right? Which is greater than zero. That means you converge to something suboptimal, right? You converge to something where every time you do something, you always wish you had done something better. If regret is sublinear with respect to the number of iterations, then the average regret goes to 0. That means we converge to predicting the optimal action. Turns out that this has strong connections to experimental design, right? So, for example, let's say in clinical trials, one way to sort of do experimental design is to split trials into sort of control, subjects into control or treatment to collect information. Most experimental designs for clinical trials are static experimental designs, which is pre-planned, right? Which is, whenever a patient or a user, quote unquote user or patient comes to our system, we randomly flip a coin, an unbiased coin of treatment or control, right? And the control is a placebo. And then we measure the outcomes, and then that's how we get an estimate of the effectiveness of the treatment, right? We get an estimate of the hidden reward of the treatment action. So this is just two-class multi-armed bandits. Multi-armed bandit says, well, okay, let's do sequential experimental design, right? Let's adapt experiments based on outcomes, right? So first person comes, we try the treatment, we see a positive outcome. So I'm simplifying to say that we can observe the outcome immediately. There's people have studied multi-armed bandit algorithms with delayed rewards. We don't see the outcome for several iterations, but that's for simplicity. Let's say we observe the outcome immediately. Patient 2 comes, we decide to give this patient a placebo, we observe a negative outcome. And then patient 3 comes, we decide to give the patient a positive treatment, we observe a positive outcome. And at this point, the algorithm should be incentivized to be biased more towards treatment options for subsequent patients, because it seems like we have evidence that the treatment is working. So basically, in standard clinical trial design, and for static experimental design, the goal is to maximize the reliability of what you learn about the system at the conclusion of the clinical trial. So at the conclusion of the trial, at some time step, capital T, in some distant future, at that point, I want to have very low error bars on my estimates of the mu's for the different actions, like treatment or control, so that subsequent policy decisions can be made reliably. Sequential experimental design says, well, hold on a second. The people in the clinical trial matter too, right? They matter as well. We should not completely ignore them. So if you start seeing early evidence that the treatment is working, you should be biasing more towards the treatment, because regret is not just about the people you treat after the clinical trial is over. It's also about the people in the clinical trial. And sequential experimental design matters, right? So this is a screenshot from a New York Times article from a few years ago where you have two cousins. They were they were genetically predisposed to a very aggressive cancer. And there was a sort of experimental drug therapy that was being in clinical trial, so they both signed up. One of them randomly got the treatment, one of them randomly got the control, one of them lived an extra 5 years, one of them died in 6 months. Right? And the doctors running the clinical trial knew that this drug was effective. Yet we still had to run a static clinical trial, 50-50 split until capital T. Obviously, there are many issues with this, like infrastructure issues, legal issues. If you let an algorithm decide who gets the drug, who doesn't, it's like the algorithm's playing God. It's to some degree. If you 50-50 split somehow fair, right? Even if it's not somehow socially maximizing the social utility. So there are other issues that I'm sort of not talking about here, but so ignoring those other issues, it's clear that sequential experimental design matters. So multi-armed bandit algorithms is a very basic model of sequential experimental design. Each treatment has an hidden expected value. You need to run trials to gather information. This is known as exploration. In hindsight, so with the benefit of hindsight, we should have always, if the treatment was good, right? With the benefit of hindsight, then we would have wished that we had treated everyone with the treatment, right? That's regret. That's the opportunity cost. This is the biggest sort of industry application of this is in online advertising, where advertisers submit ads, and people such as companies such as Google, want to surface ads as part of search results or on landing pages such as online newspapers. but you don't know how good an ad is until you try it. But you want to surface good ads because it maximizes your revenue. So this is a classic example of an exploration exploitation trade-off. Where in hindsight, you wish you had surfaced all the good ads, but when a new ad comes to the system, you don't know if it's good or not. Okay.
I have a question.
Yeah.
What's the relation between this one and the optimal optional stopping of A/B testing?
So I see. So A/B testing typically does a 50-50 split, right? It says I'm going to do a 50-50 split, and at some point I stop, right?
Yeah, optional stopping.
Yeah.
If I believe I gathered enough evidence, then I stop instead of stop after pre-decided time.
Right. So there's always a chance you're wrong, right? If you think you gathered enough evidence, let's say you're 99% sure that the treatment is effective, right? There's a 1% chance you're wrong, right?
I'm considering the difference between.
Right, I'm explaining the difference, right? If you do A/B testing with optional stopping, then your optional stopping is based on the criteria like I'm 99% confident, right?
Yeah.
Okay, that means there's a 1% chance you're wrong, right? Which means that there's a 1% chance that you suffer constant regret from stopping point to the end of time, right? Right, and that means that means you do not have a no regret algorithm, right? You actually want an algorithm that always, I mean, there's lots of infrastructure issues related to this, but with those sort of other issues sort of ignored, you want an algorithm that's always balancing between the treatment and the control. Maybe at some point, the control is sort of 0.1% of the population is getting the control, and 99.9% of the population is getting the treatment. But there's always some small chance that you might be wrong, and if you just balance it the right way, you're no regret no matter what. Right? If you do stopping, which is the standard practice, it's basically saying I'm 99% sure I'm right. 1% chance you experience constant regret to the end of time. Yeah.
Do people look at kind of Markov model of cost for multi-arm bandits? Because I imagine if you're say doing music recommendations and there isn't a uniformly best recommendation. I don't want to hear the same song.
Yeah. So there's people who do bandit algorithms with diversity constraints built into it. So I'm just going to quickly talk about one algorithm. I think it's fairly easy to explain. It takes about 5-10 minutes, and it's one of the most popular and widely used algorithms in practice these days. It's called the UCB1 algorithm. So the idea is I want to maintain confidence intervals, right? You can easily map these things to confidence intervals using tail bounds like Hoeffding inequality. So for example, if this is what we observed for politics articles, then we can sort of have this sort of tail bound on the actual reward of this article. And in this particular case, it's undefined, right? And so the more samples you have, the tighter the intervals, right? If you have infinite samples, then you've exactly recovered the expected reward. Right? They're often derived using Hoeffding inequalities. Okay, so what the UCB1 algorithm does is it says, okay, I have an expected value based on what I know about based upon what I've learned about the user so far of every action, and then I have this sort of confidence interval, right? So this is one definition of a confidence interval. T is the total iteration so far, so 70 in this example. So the sum of all these is 70. T sub k is the number of times action k was chosen. So T sub k for politics articles would be 10, right? So this would be for politics articles, this would be 0.4. This would be 70. This would be 10. This is one way of defining a confidence interval. UCB algorithm basically says at every iteration, UCB by the way stands for upper confidence bound. UCB algorithm says at every iteration, play the arm with the highest confidence bound. So, voila. One way to interpret this algorithm is that it's optimism in the face of uncertainty, right? So this is the sort of the region of which I'm confident that the reward function is in. Is sort of upper bounded by the upper confidence bound and lower bounded by the lower confidence bound. So I'm just going to be optimistic, pretend that it's the best one, that it's the best it can be, and choose that one. Right? And the way one way to think about how it balances exploration versus exploitation is so this is the exploitation term, right? This is the average reward given what I've estimated so far, and this is my uncertainty, right? So I'm just going to balance exploration and exploitation by just choosing the action that has the highest sum of average reward and uncertainty. Simple analysis. Let's see, how am I doing on time? Okay. Yeah. So let A of t1 be the action at time step t plus 1, right? So it's the one with the highest sum of average reward, empirical average reward plus this interval. Then with high probability, you know that this guy is greater than this guy. Right? So assume without loss of generality that the first arm is the best one. So we ordered it. So because this was chosen, it must be higher than this one. This is the empirical mean. And because this is an upper confidence bound, this must be higher than the actual mean of the best arm. Right? And we also know through manipulation of the confidence intervals that the utility, this is the empirical estimate of the utility. So the empirical estimate of the utility of the arm we chose plus its upper confidence bound is guaranteed to be greater than the actual utility of the best arm. The actual utility of the arm we chose is guaranteed to be lower bounded by the empirical average minus the confidence bound. Right? You put those two together, and you can bound the difference in the actual utility of the arm you chose and the utility of the best arm as twice the confidence bound, twice the confidence as the diameter of the confidence region of the arm that we chose. So we basically reduced the analysis by always selecting this, by using this as our selection criterion. We've reduced the analysis of regret, because this is regret, right? Every time step, this is the regret we pay. We've reduced the whole analysis of regret as how quickly this bound shrinks over time. And it shrinks logarithmically. So here's just one example, operational example. So here we have 5 arms. The best one is over here. So the red circle denotes the true hidden average, the hidden expected value of each reward. And the x-axis labels here how many times each arm was pulled. The blue x is the empirical average, and then this is the confidence interval. Right? This is after 500 iterations. This is after 2,000 iterations. This is after 5,000 and 25,000. Right? So a few things to notice here. First, the upper confidence bounds of all of them, because due to the nature of the algorithm, stays about the same. Right? If one of these arms had a super high upper confidence bound because it was uncertain, or let's say it was because it was uncertain, it will get chosen until it's no longer so much higher than everyone else, right? Because you're always choosing the algorithm with the highest upper confidence bound, they always stay about the same, right? Over time, the arm with the best reward, the action with the best reward, starts getting chosen exponentially more than the other ones. This sort of answers your question, right? We're always gonna have a little bit of uncertainty, right, over time. We want to have a bound over time that we don't have this rare but possible worst case, but not negative worst case scenario where we're just commit to something we're wrong, right? And so, but over time, if it actually is better, then we just do exponentially more of this, of the correct action, of the best action than all the other actions. Right. An arm never gets selected if it's upper confidence bound, so you can prove this because of how the bounds work. If it's upper confidence bound less than the actual, the reward of the best arm. Right. So if the uncertainty grows slowly over time. Sorry, this would be a mu. So this mu bar. This thing grows slowly over time, and this thing shrinks quickly with tries. That's why it gets chosen exponentially less over time. Right? So number of times a suboptimal arm is selected, you can prove, is log t over the difference squared. Which gives you the following regret guarantee. So the cumulative regret of UCB1 is at most linear the number of actions, logarithmic in the time horizon, and inverse linear in the gap between the best and second best. So the average regret is basically log t over t, which converges to 0 super quickly. And in the case where you're doing A/B testing with early stopping, there's a, let's say, 1% chance you're wrong, then there's a 1% chance that you experience constant regret over time. Okay, now obviously I've only shown you the feature-free case where there's k classes you can predict with no features, right? So there are obviously featurized version of it. These are what's actually used, for example, for like online advertising, right? You could have features of the environments, you could have features of the actions. So these are global features of the environment. These are features of specific actions. You could have feedback that's not sort of thumbs up, thumbs down, but let's say pairwise. These are all different extensions that you can consider. And so just to recap the multi-arm bandit setting, it's an interactive learning setting where you sort of learn and make predictions in a closed loop over time. And therefore you must balance the exploit and exploitation trade-off, and that the efficiency is characterized as regret and celebrated regret is good. Was there a question? Okay, so now let's talk a little bit about something a little bit more general, reinforcement learning. So I'm going to go through this fairly quickly, not a lot of details. But in the multi-arm bandit setting, one of the big sort of assumptions in the multi-arm bandit setting is that the actions you choose do not impact your state. Like if you choose an action, the reward function doesn't change. It's still the same. You just have to discover which reward function is the highest, right? The reward functions are constant over. In other words, the reward functions are constant over time. That's a very strong assumption made in the multi-arm bandit setting. In reinforcement learning, which is a generalization of multi-arm bandits, the actions you choose affect the state you're in, right? And then therefore, the reward function can drift over time, right? So here's a demo of, let's see here. So this is a learning algorithm, reinforcement learning algorithm, learning how to play Atari. So this is an AI system that's learning how to play this Atari games in the emulator. And so you see in the beginning, it hasn't estimated what's a good reward for different actions. So the actions here are move left and move right, basically. It's a two-class classification problem. But the states are all possible configurations of the game, right? So and the reward depends, and also where the ball is, right? So the reward, is highly dependent on where the ball is and where the paddle is, right? Because if you're not aligned with the ball, the reward is very low because you lose the game. And if you're aligned with the ball, the reward is high because you stay alive, right? And furthermore, in these types of settings, you actually want to model dynamics of actions, right? If you can achieve a certain sequence of states, right, actions, then you can achieve something that's really good, right? It turns out that this gives you a lot of reward, right? So if you can find a sequence of states that give you higher reward because you can learn the dynamics, then your AI system becomes very, very, very successful. So this is an instance where it's a two-class classification problem, move left or move right, right? There's only two arms that you can choose, but it highly depends on the state. Right, so in reinforcement learning, which is a generalization of multi-arm bandits, there are many, many states. So in this particular case, there's one state per image screen capture, unique image screen capture of the game. Okay. And there's two, in this case, there's basically two actions. There's two arms you can choose, left or right. And the reward of every action depends on the state, right? And the action at the current state impacts future states, right? If you hit the ball at a certain angle, it's going to come back to you at a different angle later. So your action not only impacts your immediate reward, like how many things you can hit, but the angle at which the ball comes back, so you can plan your future rewards, right? This is a strict generalization.